Okay, so intro to probability. I'm going to skip this. Honestly, the definitions make it seem more confusing than it is, and just jump into the first example. So we have a spinner with 1, 2, 3, 4, 5. All these pie pieces are about the same, are exactly the same size. So you should have just as much of a chance of landing on a 1 as a 2, as a 3, as a 4, as a 5. So nothing has got a bigger wedge than another, because that would make the probability shift. So just really basic notation. This means, what is your probability of spinning a 3? So how many 3s are there? 1 out of how many possible outcomes? 5. Basic. Your denominator is how many total outcomes are possible. Your numerator is how many of those outcomes actually satisfy what we're looking for. How about a prime number? First of all, what is a prime number? Who can define a prime number? I will then. It is a number with exactly 2 factors. 1 and itself. So is 1 a prime number? No, because it only has 1 factor. It doesn't have exactly 2 factors. It only has 1 factor, and its only factor is 1. So that's not prime, believe it or not. It's kind of a tricky one. How about 2? Yes. That's a prime number. How about 3? Yes. How about 4? No. And how about 5? Yes. So 2, 3, and 5. So of our total 5 possible outcomes, there's your denominator, 3 of them satisfy being a prime number. So there's 3/5. We have a 3/5 chance of spinning a prime number. Probabilities also can be given as decimals. So the probability on 3/5 would be 0.6. A probability also always has to be between what 2 numbers? Right, the lowest chance of something happening is 0. And the highest chance is 1 from a decimal perspective. If you think about percentages, when you talk about percentage chance, the lowest is 0%, the highest is a 100% chance. Yes? Okay. How about, what is your probability of spinning a 1 or a 5? So, first of all, there's still 5 possible outcomes. How many of them satisfy being either a 1 or a 5? 2. I will also say this on this problem. Or in probability, you should equate with addition. So I can look at those 2 events separately, like the probability of spinning a 1 plus the probability of spinning a 5, and that's 1/5 plus 1/5, which gives you 2/5. What about the probability of an even or a prime? So there are still 5 outcomes. Is this one even or prime? No. Is this one even or prime? Yes. 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 So 4 out of the 5 will make me a winner here. Now, what's interesting on this one is that if I use that addition concept and I look at the probability of an even plus the probability of being prime, what is the probability of just being even? 2 out of 5. Plus, what's the probability of being prime? We did that up here, 3 out of 5. Doing it that way gives me 5 out of 5, which is wrong. Why did that happen? Nate. I'm only going to call them someone because they had their hand up. Right, we double counted something. The number 2 we counted as being an even number, and it was also a prime number, so we kind of double counted it, and this makes us think that we have a 5 out of 5 chance, meaning a 100% chance of this happening, which is not true. We definitely don't have a 100% chance of it happening because there's always the possibility that we spin a 1, which would not make us a winner. So the rule here is we also have to subtract anything that was in both categories, right? The probability of spinning something that was both of those things, so finding anything that was in both categories, because we double counted it, so we have to subtract it off. And the only number that was in both categories was 2. So we have to subtract off 1 out of 5 because 1 out of the 5 of those was in both categories and got double counted. So I really am undouble counting it. And then it would work. This one I didn't have to worry about this because were there any numbers that were both a 1 and a 5? So minus the probability of both? That just never happened. So we subtract off 0 out of 5 and it didn't affect us there. So if the or events are, and the word is mutually exclusive of each other, meaning there's no overlap, okay, then you don't really have to worry about subtracting. So these events are mutually exclusive events. That's a vocab word. And these events here were overlapping. I say just always assume there might be an overlap and think about it. Okay, so or probability does mean add, but you always have to remember to subtract any overlaps. So already it gets a little bit more complicated than probably what you were used to in 6th or 5th grade. Now, and probability. And in probability means multiplication. So now I'm not just spinning the spinner one time. If I'm going to get a 1 and a 3, now I'm spinning it on 2 occasions. The or is I'm spinning it one time and I have a lot of options. The and probability means I'm spinning it multiple times and I'm looking for something very specific to happen the first time and for something very specific to happen the second time, which means my probabilities tend to get less likely because I'm stacking these stipulations on. Okay? So, and means multiplication. So what is my probability if on my first event, I'm spinning the spinner, my probability of getting a 1 is 1 out of 5. And then I'm going to spin it a second time. So there's my and means multiplication. And my probability of spinning a 3 is also 1 out of 5. So really the probability of both of these things lining up and happening is 1 out of 25, which is not great. Okay, the more events you stack on, the less likely your chances are. It's like if you think about baseball and you think, okay, you know, my team can win this game if the next person gets up and hits a home run. Okay, that's not likely, but it's possible. Versus, okay, now my team will win if the next 3 batters get up and hit a home run. He has to hit a home run, and he has to hit a home run, and he has to hit a home run. Now you're talking like, really, that's not likely. You could look at March Madness right now. I will win my tournament if Duke wins and I win. Versus, okay, I can win my bracket if Duke wins and this person loses and this person wins. The more ands you throw on there, your probability is going way, way down. Does that make sense? Nathan? It depends on if you're going with theoretical probability. In theory, yes. But in... Right. But from what the results you've seen, the answer would be no, because it hasn't happened yet. So maybe like that gets a little tricky. If you talk to my grandma, the probability of winning the lottery is 50-50. Either you win or you lose. Right? Like it's just a play on probability. Like obviously that's very wrong. We all know that the probability of me winning the raffle last night at the spaghetti dinner was 1 out of 52. because I had the king of diamonds. But that did not get called. Anyway, we move on. Decks of cards will be very common here. All right, probability of being even. So on my first spin, what are the chances that I'm even? 2 out of 5. And multiplication, the probability of a 4. 1 over 5. This is not a double count situation because it's not an or probability. These are two totally separate spins. The first chance, even, I'm looking for an even the first spin, and then on the second spin, I'm looking for a 4. So that would be 2 out of 25. You don't have to worry about that subtraction with or probability. Now, I will get a little bit ahead of myself, and I will tell you that we will soon find out that this straightforward multiplication, when you see and, only works if the events are totally independent of each other. Meaning, whatever I spin the first time has absolutely no bearing on what I'm about to spin the second time. Okay? Those are two totally different and independent events. And because they are independent, and just turns to multiplication. Okay? We will get to instances where there's not independent events, meaning they're dependent on each other. And that would be like, let's say you pick a deck of cards. Your probability of picking a heart, and then your probability of picking a heart again. So if you take the deck and you pick a heart out, and then you don't replace that card, now the probability on the second time is affected because you no longer have 52 cards in the deck because you left that card out. Now you only have 51. So a second event can be dependent on the first event, in which case this and probability wouldn't work. This and multiplication wouldn't be as straightforward, but we will get there. All right, so a couple vocab words. What is the experiment? The experiment is spinning the spinner. An example of an outcome, I don't know, 3. That's a potential outcome. And an example of an event would be like, could be like the probability of an even. The sample space, okay? The sample space is your possible outcomes. So if you're spinning the spinner just one time, your sample space is either you're going to get a 1, your outcome could be a 2, your outcome could be a 3, a 4, or a 5. The sample space is just a list of the possible outcomes. So those are the 5 possible outcomes if you're only spinning the spinner once. Now, if you're spinning the spinner twice, your list of outcomes becomes much greater. You could get a 1 and a 1. Or you could get a 1 and then a 2. Or you could spin a 1 and then a 3. So on and so forth. Then you could spin a 2 and a 1. Spinning a 1 and then a 2 might be different than spinning a 2 and then a 1. So depending on the types of problems and the way that they phrase it moving forward, we'll have to look at that. Is a 1 and then a 2 a different outcome than a 2 and then a 1? Sometimes it is, sometimes it isn't. Depends on the experiment. So on and so forth until you get all the way up to a 5 and then a 5. Don't read that as 11. Do you follow what I'm saying? I know it looks like 11, but hearing me talk through it, that's like a 1 and then a 1. Maybe I could have written it like 1, 1, 1, comma, 1, 2, comma. So don't try not to think of that as an 11. Isaiah. They could. How many different total possible outcomes are there? They could, and there will be a shortcut because you won't have. It will get crazy fast, right? You can see that already with just 2 spins. Does anybody know how many outcomes there are for 2 spins? As long as we're treating 1 and then a 2 different than a 2 and then a 1. Does anybody know how many will be in that full list? 25. Yep. Because 1, 1 through 1, 5 is 5. And then you got to do 2, 1 through 2, 5. That's 5 more. And you're doing it up to 5. So it will be 25. We'll get into that. We already talked about this one. The minimum of any probability is 0. The maximum is 1. Okay? This is what kind of, Nathan, we were talking about earlier, theoretical versus empirical. Theoretical means based on theory. So if you're flipping a coin, the probability of getting a heads is 1 out of 2. There's 2 total outcomes, heads or tails, and only one of them satisfies being a heads. So in theory, 1/2. But let's say empirical probability means you've already flipped the coin 100 times. Let's say you've taken this coin and you've flipped it 100 times, and 99 of them were heads, and only one of them was tails. Now, if you're about to flip that coin, empirically, you would say your probability is 99 out of 100 is your probability of getting a heads. So empirical makes you base it on previous results. Now, obviously, in this case, we would be suspicious of the coin, right? Is it weighted funny? You know? But if you're going to base it on empirical probability, you would go that way with it. Okay? And so, again, depending on the situation, you might choose to follow your theoretical gut versus you might choose to follow your what the empirical evidence has shown you. Okay? Have you heard the word empirical in science class? All right. A coin is flipped 3 times. So we have 3 events, okay, that are kind of being stacked on each other. Draw a tree diagram that's really going to help us model how many possible outcomes there are. So on your first flip, you're going to get a heads or a tail. I don't know. I did tails or heads. Why I did that. So this is event 1. That's your first flip. Now, event 2 is going to be the next tier. So if I got a tails on the first one, on my second one, I can also get a tails or a head. Or if I got a heads the first time, when I go to flip the second coin, again, I could get a tails or a head. And then event 3 is my third tier. Let's pretend I got a tails and a tails. My third one could be tails or head. And so you get a tails or head branch off of each of these. That's why they call it a tree, because it's kind of like branches. So at the end of all this, if you count your last tier, 1, 2, 3, 4, 5, 6, 7, 8, there are 8 different items in your sample space. Okay? The possible results from flipping 3 times are tails, 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 head, tails, heads, tails, tails, heads, heads. And that's all if I flipped a tails on the first one. Then I got to go through all my H's. Heads, tails, tails. I'm really just going down each avenue to get to the bottom. And by the end of all this list, HHH would be my last list item. Now, how could you get there? Your shortcut, Isaiah, is something called the basic counting principle. Event 1 has 2 options. So 2 times. Off of each of those 2 options, event 2 has 2 more options, times 2. And then off of each of those, we branch off 2 more times, so event 3 has 2 options, and 2 times 2 times 2 is 8. And that's where you would get that number from. Does that make sense? So if we go back to this last one, and we were, what were we doing? We were spinning twice. The first outcome, the first spin has 5 possible outcomes. The second spin has 5 more possible outcomes. 5 times 5 is 25. Yeah, but on some cases we'll do something like you've got 5 shirts, 4 pairs of pants, and 2 pairs of socks. How many outfits could you make? And it will just be 5 times 4 times 2. So that what you said would be okay for this situation, but this basic counting principle goes beyond that. So let's see, we got 2 minutes. So this would just be all out of 8. All heads would be, there's only 1 out of 8 that's all heads. Exactly 2 heads. Not this one, not this one. Here's an exactly 2 heads. Here's an exactly 2 heads. Then when we get over here, there's another exactly 2 heads. You just kind of got to go through your list. There's another exactly 2 heads. So that would be 4 out of 8, which reduces to a half. Now, the last one, all heads or all tails, there's where your addition is going to come in. 1 out of 8 are all heads, plus 1 out of 8 are all tails. Is there any outcome that's both all heads and all tails that we have to worry about an overlap for? No, there's no way you could get all heads and all tails. So this would just be 2/8, which would reduce to 1/4. You should always get in the habit of reducing, okay? So I'm not going to give you a spiral today because your corrections or your sequences quiz, I'm going to collect on Monday, okay? So you have your quizzes, and for some reason you don't, I must still have it. But your homework and your second weekend assignment is your sequence corrections, which I know some of you already have done. Good for you. Some of you lost, of course. If that's the case, Jordan, I will give you a blank copy and then just review the quiz first. So you don't lose. But if you lost your quiz, I don't know which 2 they were. So in a case like that, I just say,